As you probably know, machine learning is all the rage nowadays, and one component of machine learning is neural networks. So we're going to take a look at how the composite design pattern can show up in the simple simulation of neurons and neuron layers and how they're connected. So let's suppose I make a class called neuron. Now what I want to do is I want to have some sort of value for this neuron, so I might as well make a public value. We're not going to be using it though, because what I want is I want the connection from this neuron to other neurons, and also want to track the connections which are incoming. So we have two sets of connections coming in and connections going out. So for this I can make two lists. So I can have a list of neuron, and I'll have two lists, one called in and the other called out. So this is very simple. You have lots and lots of neurons. They're all connected to one another, and typically the way that you connect one neuron to another is something like the following. So you have a method called connect to, and this method connects one neuron to another. So you have neuron other, and then of course you add this neuron to your outgoing connection. So you say out.add other, and then on the other neuron you add the incoming connection. So you say other.in.add this. Okay, so this is how you connect a single neuron to some other neuron. So we can make them. So I can say var neuron 1 equals new neuron. There we go. And I can make neuron 2 as well. And for now everything is fantastic, because I can say neuron 1 dot connect to neuron 2, and everything is fine. I mean, this is completely legitimate code. Everything is correct. You know, it's working perfectly. Now, I'm going to throw the spanner in the works here. What I'm going to do is I'm going to add a neuron layer. Now, a neuron layer is quite simply a collection of neurons. It's a collection of neurons, and the thing about this collection is you also want it to be connectable to things. So I'm going to make a new class called neuron layer, and here I'm going to implement a collection of neurons. Have collection of neurons. Okay, could have been a list or something else, but you know, let's keep it as collection. And now we have a very big problem, because now the connectivity is still required. So if I have also a bunch of layers, so if I have layer 1 equals new neuron layer, and if I have layer 2, I have the requirements that I can connect a neuron to a neuron. That's already handled, a neuron to a layer to a neuron, or a layer to a layer. So instead of just one method like we have here, we now need, or it looks like we need 4 separate methods to actually connect every kind of object to any other kind of object. Because remember, a neuron layer is just a bunch of neurons, so we want to take every neuron, for example, from a layer and connect it to some other neuron. But we cannot, because we don't have the API for this, and we can certainly start writing for each loops and whatever. But imagine that later on, somewhere down the line, you have a class called neuron ring, which also does something different. It's not a collection of neurons. It could be like a list of neurons or something. And then you're in trouble once again, because then the explosion of this number of different methods, different permutations, is too much. And you don't want to deal with this. You want to apply the composite pattern, but the question is, how do you apply it? Now, I'm going to surprise you here and tell you that you can keep a scenario where you have just a single method covering all of these. Now, the way that you do this is by using an extension method, and the question is, well, an extension method on what? What is in common between a neuron, which has no base classes and is just a standalone class, and the neuron layer, whose base class is already occupied? So it's not like we can give both of these classes a base class. We cannot do it because this class already has a base class. So what do we do? And the answer is that we simply treat both neuron layer and neuron as a collection of neurons. In the case of a neuron layer, it's obviously a collection already, but in the case of a neuron, we can also treat it as a collection of just a single element. So the question is, well, what do we do? Do we have to inherit from collection of neuron here in a single neuron? And the answer is no, you don't have to do this, because essentially in the .NET framework, we already have a paradigm, we already have an interface for expressing the idea of enumeration, and that is of course IEnumerable. Now in the case of a neuron layer, it's a collection, so it already implements IEnumerable, no problem here. In the case of a neuron, we simply implement IEnumerable like this. So we say a neuron is an IEnumerable of neuron, and then of course we have to implement the missing members. the get enumerator, both of these varieties, and here the default implementation is just to get the strongly typed variety, so we only have to implement one method. Now typically in get enumerator is where you return each of the containing elements, but here we have a scalar, so neuron is a scalar value and we want to represent it as an IEnumerable. So the only way this can be done is by yield return this. So we yield return ourselves as the one and only element which is actually providing an enumerator. So this is great because now a neuron is an IEnumerable and the neuron layer is also an IEnumerable, and what this means is we can now write an extension method on IEnumerables. So here we'll have a static class called extension methods, and I'm going to have a public static void connect to. So instead of having connect to down here, for a single neuron, I'm going to get rid of this. We're going to implement this for any two collections of neurons. So we have the left hand side, this IEnumerable of neuron, let's call it self, and then we have IEnumerable of neuron other as the right hand side. And what we do is we iterate through all of the neurons in the self, all of the neurons in the other, and we connect them together. So we say, well, first of all, we check for referential equality because they're very equal. We don't have to do anything. So if reference equals self and other, then simply return. But if not, what we do is we say for each var from in self, for each var2 in other, and this is where we can actually do some work. So we say from dot out dot add 2, and then 2 dot in dot add from. There we go. The indentation is a bit broken here, but here is the implementation which will work in all of these scenarios. So what you'll see here is that we now have a way of connecting, let's say, a neuron to a layer. Neuron 1 connect to layer 1. This is completely legal now because both of these, both neuron 1 and layer 1, are IEnumerable of neuron, because essentially a single scalar neuron is masquerading as an enumeration by yield returning itself, yield returning this. And of course we can connect layers to layers, for example. So we can say layer 1 dot connect to layer 2. So as you can see with the composite design pattern, once again, you can make sure that even scalar values are treated as composite values or with singular content, and that way you can write very generalized algorithms on both singular as well as composite values.